My name is JJ Zanazzi, and I'm a postdoctoral fellow now at the Canadian Institute for Theoretical Astrophysics. And today what I'm going to talk about is work I did as a PhD student under my previous advisor, Professor Dong Lai at Cornell, on the dynamics of protoplanetary disks in stardust binary systems. Oh, okay. Here's the clicker. Okay, so the main observation motivating the work which I'm going to be discussing today are the many exoplanetary systems which have been observed where the orbital angular momentum axis of the exoplanet is highly misaligned with the host star star spin axis. And the main way people have conventionally explained these exoplanetary systems is through formation from the high eccentricity channel, where the planet forms and undergoes some violent gravitational interaction, which places the planet on a highly eccentric orbit inclined with respect to the equatorial plane of its host star. And then tides work to circularize the orbit to leave a close-in short period planet which is misaligned with the equatorial plane of the host star which it formed in. This is not going to be the focus of today's talk today. Instead, what I'm going to talk about is an alternative formation channel known as primordial misalignment, which argues that the misalignment between the exoplanet and its host star occurs while the exoplanet is still forming in its natal protoplanetary disk. And the specific mechanism which I'm going to discuss today is the gravitational torque acting on the protoplanetary disk, where the planet is still forming in, by an inclined binary companion. But before I discuss how my work fits into the picture, I'm going to discuss the picture itself, which led up to my work, which was pioneering work done by Konstantin Batygin and my previous advisor Dong Lai, among many others. At the center of the system, we have a spinning oblate star with stellar spin axis S hat, surrounded by a circumstellar disk with orbital angular momentum axis L hats of D, with a distant inclined binary companion with orbital angular momentum axis L hats of V. The binary companion exerts a gravitational torque on the circumstellar disk, causing the disk to precess around the binary's orbital angular momentum axis with a precession frequency, which we're going to call omega dB. And this precession frequency has a precession period of order 1,000,000 years. And in addition to this gravitational torque, there's also the gravitational torque exerted on the spinning oblate star by the circumstellar disk, causing the star to precess around the disk's orbital angular momentum axis with a precession frequency, which we're going to call omega SD. And the important thing to note about this precession frequency is it's proportional to the disk's mass. So when the system first forms, the disk has a whole lot of mass, and omega SD is significantly larger than omega dB, and so the star is very tightly coupled to the disk's orbital angular momentum axis. But as the system evolves, the disk loses mass, either the turbulent viscosity or disk wins or whatever, and eventually these two frequencies become comparable to one another. And when this happens, there's a large amount of angular momentum which is transferred from the inclined binary companion to the mutually coupled star disk system. And when this occurs, the system undergoes what's called a secular resonance. And this secular resonance has a big impact on the mutual inclination between the host star and the disk, and can significantly excite large exoplanetary obliquities with respect to the host star while it's still forming in the disk. So in this example, we have an initial star disk binary inclination of only 10 degrees and an only slightly misaligned disk with respect to its host star. And after secular resonance occurs, we are able to excite stellar obliquities up order 50 to 60 degrees. So this is a very robust mechanism. But what had not been done before I entered the picture is looked at how the exoplanet actually forming the system modifies the dynamics, since this is the thing that we actually observe after the disk dissipates. So that's what I'm going to discuss now, how a short period massive planet forming the system modifies the dynamics. So the system which we're going to think about now is the same as before, except now we have a massive short period planet forming the system with orbital angular momentum axis, which is L hats of P. Because the main effect of this forming planet is to exert a gravitational force on torque on the spinning host star. This forming planet modifies the gravitation, causes the star to precess on the planet's orbital angular momentum axis with a precession frequency we're going to call omega SP, which is a precession period also of order 1,000,000 years. Because of a mess of planet-disk interactions, which were discussed previously, we can in this conference, and in addition in my paper, we can very safely assume that the planet is tightly coupled to the disk, which means the main effect of this forming planet is to modify the precession frequency of the host star around the disk's orbital angular momentum axis, with a precession frequency which we're going to call from now on omega SD prime. So in order for the system at some point in its evolution to undergo secular resonance, this new modified precession frequency must at some point in evolution be less than the disk binary precession frequency. And this inequality places a very stringent lower bound on the semi-major axis of a forming planet, below which a planet will remain spin orbit aligned with respect to its host star, even in the presence of an inclined binary companion. And the very important thing to note about this very stringent lower bound is this is significantly larger than all hot Jupiter semi-major axes detected to date, or which have semi-major axes less than about 0.1 AU. And these are the primary planets which we observe to have spin orbit misalignment within them. Okay, so to demonstrate this effect in action, I'm going to look at the simplest possible example, which is where the exoplanet forms at the location we observe it today, or in situ formation. So the thick black line here shows when you have a massive planet forming at a semi-major axis of about 0.07 AU. Because it forms so close to its host star, the host star never decouples from the disk's orbital angular momentum axis, and you never have secular resonance occur in the system, and the negligible stellar obliquities are generated by the end of the system's lifetime. The thin blue line shows what happens when you have an exoplanet forming further away from its host star with a semi-major axis of about 0.25 AU. And because it's much further away, eventually, as the system evolves, the stellar spin decouples from the orbital angular momentum axis, and stellar obliquities are excited in the system. But the important thing to note about this example is that it's not a hot Jupiter, which are the primary exoplanets we observe to have spin misalignments within them. Okay, so I considered a whole bunch of different formation pathways for this work, and I don't have time to discuss every single one of them. But the important thing to take away from this work is for every single one of these formation pathways I have on the right-hand panel here, the formation of a massive short-period planet before the disk dissipates usually reduces and may completely suppress the excitation of stellar obliquities by the inclined binary companion. But there's a really strange caveat to this work in that this mechanism is still very, very robust for systems of low-mass multi-planet systems forming within the protoplanetary disks, and cold Jupiters, which form much further away from their host stars. And like Rebecca mentioned, there's many disks with inclined binary companions, and so we should actually this mechanism should still work for these types of systems. But if you look at the observations, observationally, these systems tend to be actually aligned with the equatorial plane of their host stars. So why is this mechanism really good at generating stellar obliquities which you don't see? One possible way to get around this is some effect actually works to damp the stellar obliquities after they're excited by an inclined binary companion. And one possible mechanism, which I'm going to discuss next, are dissipative torques from viscous torques from dissipation from disk warping. Okay, so that's what I'm going to discuss now, how viscous torques from disk warping work to modify the long-term evolution of these star-disk binary systems. But before I discuss the details of how viscous torques from disk warping affect the long-term evolution of star-disk binary systems, I'm going to draw an analogy with something I think a lot of people are more familiar with, which is equilibrium tides and binary systems. So instead of a disk, let's now consider a fluid body which is being perturbed by some perturber. And when the amount of dissipation is very, very small, the tidal bulge excited by the perturber exactly follows the perturber's location as it orbits its fluid body host. And because there's no dissipation, there's no phase lag, and so there's no tidal torque exerted on the host by the perturber to leading order. However, there is a tiny little bit of dissipation, and this tiny little bit of dissipation exerts a back reaction torque on the host, and this back reaction torque works to either spin up or spin down the host. It either works to drive in or out the semi-major axis, and it works to either pump up or pump down the eccentricity of the orbits of the perturber with respect to the host. And it turns out that viscous torques from disk warping work in basically exactly the same way, because to leading order, these protoplanetary disks are very hot, and this means that bending waves work to very efficiently smooth any disturbance induced on the disk by the oblate star or the binary companions. So to leading order, we can very effectively approximate this disk as a rigid plate being torqued externally by the binary companion or the spinning host star. However, the disk is not totally flat. It has a small twist, which means that the inner angular momentum of the disk is slightly misaligned with respect to the outer angular momentum direction of the disk. And this tiny twist exerts a back reaction torque on the disk which is on the disk by the binary companion as well as the spinning host star. And this effect is, this twist induced on the disk is proportional to the disk viscosity parameter, inversely proportional to the disk temperature, and proportional to the precession period of whatever torque is being exerted on the disk to the second power. Okay. Now, specifically, how I calculated the viscous torques from disk warping acting on the systems, I did a perturbative calculation, assuming to leading order the disk is totally flat and rigid with a small correction to the disk's small disk warp. And then once the disk warp was actually calculated, you can calculate the viscous torques from disk warping actually working to modify the long-term dynamics of the star disk binary system. Okay, so here are the key results. So all these different lines are just different disk models. So if there's a small spread in lines, that means that the damping rates of the star of the disk with respect to the binary, or the star with respect to the disk, depends a lot on the disk parameters you assume. There's a small spread, it doesn't depend very sensitively. And so you see, unfortunately, for for most of the parameters of interest for star disk binary systems, these damping rates are significantly longer or significantly shorter than the inverse of the disk's lifetime, which means that these effects are typically not very relevant for typical protoplanetary disk systems with binary companions. However, if you have a sufficiently strong external torque, which means that you have a sufficiently close binary or a sufficiently rapidly spinning star, these effects actually can be important in the long-term dynamics of the star disk binary system, and they can work to significantly reduce the stellar obliquities, which were originally excited by the inclined binary companion's gravitational torque. And so here are a few examples showing what happens to the system evolution if these effects are actually important. The left-hand panel is when the damping rate between the star and the disk is high. The middle panel is when the damping rate between the disk and the binary is high. And the last panel is when the damping rate of the star between the disk and the disk between the binary are high. And the important line to look at is the blue line, which is the stellar obliquity, which we actually see once the disk dissipates. And you see for every single one of these examples, the inclusion of these viscous torques from disk warping work to significantly reduce the stellar obliquities, which are excited by the binary companion. And we may need to actually invoke these to explain why we see exoplanetary systems with binary companions which have low stellar obliquities. Okay, so here are the two main takeaways of my work. So for the first main takeaway is if you have a hot Jupiter forming in a star disk binary system, the formation of this hot Jupiter itself actually works to significantly reduce or completely suppress the excitation of obliquities by the inclined binary companion's gravitational torque. And the second main takeaway is viscous torques from disk warping are typically not very important in the long-term dynamical evolution of star disk binary systems. But if you have sufficiently strong external torques in a sufficiently cold disk, these effects might actually be important in the long-term evolution, and we may need to invoke them to explain the low stellar obliquities we see in these systems. Okay.
Thanks a lot, especially for keeping the time. Questions? I might start with a question regarding the importance of viscous torque. So you used an alpha of 10 to the minus 2.
Yep.
Would you still find the same result if you use the 10 to the minus 3 or 4, which is what is typically now considered to be the value?
Yeah. So if you lower the alpha, that'll lower the damping rate significantly, and so the effects will be even less important. Yeah. So it's going to be proportional to the alpha that you use all these effects. Yep.
So if you want to use this viscous torque to explain the absence of the obliquity, you need a large alpha.
Yeah, you do need a very large alpha to explain it. Yeah, 10 to the minus 2.
Okay. Okay. Other questions? Okay, no. If not, we can move on to the next talk. Thanks a lot.